me first of all try to give some background what this is about, because it has been sort of implicitly studied before. So just to go back in history a little bit, so in the 70s, Brunault was sort of inspired by the classical relation to the regulator of the units in the ring of images of a number field, and the let's do it as equals 1 corresponding zeta function. We'll have defined higher k groups, and then one of the k groups came out, k1 of the ring of images of a number field is the unit group. So they then wanted if there was a similar relation between regulators of higher k groups and the values of zeta functions at other points. So the answer was yes, and I think that's true for the all k groups here, not k1. So in that case, the k3, k5, etc. the field is the same as for the ring of integers. Fully proof this is finally generated. So
there's no question about torsion.
sorry?
I didn't know. I thought that was only true after you tensor with Q.
No, that's true. Sorry. The point is that this one, the OF injects into Kn minus 1F always, and then the next one we even can define a field which is going to be 0. Not K0. So he defined a regulator map using a homology class of GL, because you can map the K groups into some H n GLN or H2 n minus 1 GL2 n minus 1 in this case. And then he computed that if you do this, you get a regulator comparing the bases of the K group with suitable bases inside, say, R to some power. And then he related this regulator to the for the string dot to the big value at n. So for example, for Q, the first one is K3 of Q, which is finite. And then this relates to zeta2, which is pi squared over 6, very simple number. And then the next was K5, which is rank 1. I don't know the torsion, probably trivial. K5 for Z, is that? Okay. So it's exactly just cyclic without any torsion, that it relates to zeta3, which is much harder. So that's the kind of pattern that fits here. So Spencer, then not much later, thought, hey, maybe we can do something like this for elliptic curves. He took CM elliptic curves over Q, defined an element in K2, let's say tensor with Q for simplicity, and produced an ad hoc regulator, at least in those days ad hoc, and related this to the alpha with the function at 2. So then Beilinson came along, and he sort of in the introduction of this paper says, you know, I tried to understand Worrell's results and Bloch's results, and then he apparently understood it rather well, because he came up with an enormous generalization relating K groups and regulators to special values of alpha functions, and provided ample evidence. So there was actually a slight error in the beginning, namely that they worked with the K group of the variety over the number field, but they should have really worked with the image of the K group of model, a nice regular model focusing over the ring of integers, which you know exists for curves, but then for higher dimensional this is not known. But then show at some stage that you can use alterations to make up for this deficit. Okay, let's switch a little bit to curves, and I'm not going to claim an overview, to give an overview of what has been done, so maybe a taste. So first of all, Beilinsons, when he proposed his conjectures, proved that you can get enough elements for his conjecture, plus they give a regulator with the expected relation with the L function. In fact, he decomposed the entire thing according to Hecke decompositions, etc. So it's much more subtle than what I've written here. Deininger did something like this for certain C element curves over number fields, but then not for K2, but also for K4, etc. Then I gave an example in a paper in '96 for K4, which is much harder to get your hands on. It relates very much to what Karin was talking about yesterday. And then a numerical relation with the corresponding L value of 1. I'll get back to the star later. Then with Tim Dockschützer and Don, also present here, we tried to get away from the sort of elliptic modular world. So we used hyperelliptic curves. I'll say something about this later as well. And then there have been various results by other people who looked at various situations. So K2 is way more popular than K4, let alone K6. So one thing you can get if you
was it done? No, it wasn't me.
was me, that was me.
Ah.
I was just pushing the wrong button.
Intentional.
Well, I was not intentionally pushing the wrong button. I was intentionally pushing the button, but not intentionally the right one. Anyway. So if you have a strongly modular curve, so you can cover it by a modular curve, then you can also, well, this is the standard trick to get elements in K2. In this case, basically, you take 2 points on the curve, which the difference is torsion and Jacobian. That's sort of the most basic way of getting something. So if you model curves, then the difference of 2 cusps will satisfy this. So this will give you ways of constructing elements, but then the trouble is everything is going to be defined over some cyclotomic field, and therefore you'll never get out of, say, number fields, base fields that are abelian. So that is part of the thing for this talk. Okay, now I see what. Okay. So that's really one of the things for this talk, that we get away from this abelian base field. Okay, so what do we need? So I first of all reviewed K2 up there for any fields, but I suspect in this world this may be done. So what are the cases that we want? Well, K2 of the curve is actually quite hard to describe explicitly. You've got to work with the quotient, the kernel of the tame symbol. So you look at the K2 of the function field, and then for every symbol f, g. It's probably strange.
Uh-huh.
Are you doing that, or is it doing that?
No, I was doing it. Probably if you hold it too long, it will do that or something. Anyway, so to every class in the tensor product f, g, you of a, b, you associate this thing on something, a point of codimension 1 in your curve or in your surface. So if you look at your model, nice, regular, flat, and proper, then the codimension 1 points there either correspond to the codimension 1 points on the generic fiber, and using the tame symbol there, it's basically using the same symbol on the generic fiber, and then you also get the components in the fibers of your model, and that will give you additional conditions to get sort of the what people, I think, annoyingly call the integral subgroup, right? The elements that come from left in the long run. And just to clarify one thing, you have to make a choice of model to take this, but it turns out that actually if you look at the image of this thing, of the K2 of your model, inside the K2 of your function field on the localization, then this is independent of the choice of your model. So it's convenient. You don't have to ignore any torsion or anything. Okay, so what is the Beilinsons conjecture about? So let's start with the curve over the complex numbers. And many thanks to Vadin for dealing with this slide mostly. So you take a nice regular proper curve, you take an element in the kernel of the tame symbol, take a loop or a sum of loops on the curve, and then you pair the loop and the element in K2, the kernel of the tame symbol by, well, you write down this eta, which Vadin also wrote down. And then the fact that you're in the kernel of the tame symbol means that the residue of this thing at every point will be trivial. So that means you can sort of, as long as you avoid loops in your functions, zero-sum in your functions, you can just take any loop on your curve and then integrate the one form, and the result will be independent of the loop in, at least the representative of the loop in its class. So how are you going to put this together if you work over a number field? So again, you take a nice curve, but now over a number field. And let's just say that the number field f consists of the constant function, so you sort of know what is going on if you go through the complex numbers. If this degree is m, you then extend the complex numbers, you get m Riemann surfaces, all of the same genus G as the original curve. And well, then to get the correct behavior, you look at complex conjugation, right? You embed your number field into the complex numbers. You can let conjugation act there. And then, well, the total H1 is of dimension 2 times m times g. And the invariants are sort of half of that, at least the rank is half of that. So you can then do the pairing that also, well, that involves what we just did for the complex numbers. right? So an H1 element in H1 of this union of Riemann surfaces X is just a bunch of H1s on the actual components. So you take the element in the kernel of the tame symbol over the base field, you pull it back over the complex numbers using your embedding, and then you compare on that Riemann surface what you in the way we did this before. So I cannot stick to the base field being Q because Q is Abelian over Q, so that wouldn't work. I have to introduce notation for the embeddings. Okay, so in order to get the statement for the Beilinson conjecture for K2, so we assume that the L function of the curve has a nice functional equation relating S and 2 minus S. And then if this functional equation has the correct shape, then the first non-vanishing coefficient in the Taylor expansion of the L function is 0. Or it should have a 0 of order n, which is the rank of this H1 minus we just talked about. And okay, then Beilinson tends it with Q. So Beilinson said take a K group, it's K to C tensor with Q, and then its Q dimension should be equal to the n. So, but it's also a conjecture of Best, which would imply that this thing is actually going to be finally generated. So let's make it a little sharper in that sense. So let's believe that this kernel of the tame symbol on the model is.
But why are you assuming, and it's completely out of reach, the Hausdorff conjecture and analytic continuation? You can always talk of L of 2, which is always well defined. Why?
Yeah, but then of course we have to.
Conjecture too. You can say L star of C0 is the
Sure,
thing which would be L star of C0 the function equates to true, but you don't need the conjecture to define it.
Sure, but actually in that case this number, this rational number Q becomes more complicated.
No,
and,
it's the same number. You define L star of C0 as a multiple of L of C2, the one that's predicted by the function equation. You don't have to know that it is L star of C. It's the same number.
Sure, but the conductor is part of the functional equation, right? The conductor shows up if I formulate this as 2 as well as vectors 2 pi.
The conductor is defined without assuming the Hausdorff conjecture.
Sure. Okay.
I just don't understand why you're assuming the analytic continuation.
Well, I do it because Beilinson did it, roughly speaking. No, okay, you're right, of course you can just unformulate this, but then you get something that will involve the conductor, etc. And then you can put the conductor in there. No, the reason actually I'm formulating like this is that I'm thinking ahead for and then Lichtenberg conjecture, even for numbers, you're not going to formulate at 2 or 3, etc. You do this using the functional equation at negative integers to get clean of the numbers, and that will be part of the game here. So the conductor is unique in that sense. Okay, and I think I forgot to say what the point was. So you take supposedly the z basis of your K2, the integer elements in your curve, so supposed to be rank n. The H1 minus of the union of Riemann surface also has rank n. And then this pairing that we had is supposed to be non-degenerate. And if you then compute its determinant, and you have to tell me you get a well-defined number, and that should be relating to this L star at 0 in this way. The rational number, non-zero rational number times is regulated. And of course you can indeed rewrite it if you like to formulate into LC2. Okay, let me just say a few things about what happens, because it's a way of, if you look at the curve of Q, you need only one element. And if you make a higher genus or you go to a higher dimensional field, so you have to produce more elements. So this is sort of the first attempt maybe to get away from elliptic curve of a Q using hyperelliptic. I'm borrowing modular curves where you can do a lot more. So you basically write down a clever equation of a hyperelliptic curve. So you can see it sort of in a non-complete and of the square way. So you can look at what happens for the prime 2 and the reduction. And then it's just a matter of sort of writing down clever ones. We have various families in this paper of 2006 with Tim Dobsches and Don Zagay. And so if you take your f to be of this particular shape, so you start with this 2x to the power g plus 1 and then some linear factors. If you were to look at the equation, you're going to complete a square in y, then you end up with y squared equals something, and that something is actually written here, minus 2g plus 2 x about 2 plus that. This is just the difference of two squares, so you have an obvious factorization, and then the linear factors will come out as, so this one has many y plus points that are rational over the base field. On the end, if you put y equal to minus fx, then you also see there's only one point of intersection, and this will be a torsion point on the Jacobi. There's one point of infinity if you use that one as the origin. So as I say from the beginning, so one of the standard tricks is suppose I take a function and I have sort of 3 points p and q and o. I suppose that p, q, and o are distinct. And you look at those differences. I suppose there are n torsion order dividing n, and I normalize my functions to be wrong at p and q, then you actually see that your symbol f, g, will be in the kernel of the tame symbol. And so this is the most basic construction, because the tame symbol has been made wrong at p and q by construction, and it could only be non-trivial at O, but there's a product form that will be trivial there too. So that's what's going on here. Just write down a curve with many torsion points, and then you can get many elements in the kernel of the tame symbol. And we produce, I think, 200 curves for actual calculations, where we computed this relation with L star. And also proved later on that actually, if you sort of fix almost all parameters and let one go to infinity, then the elements you produce are actually independent. And also, I should say, forgot, of course, the integrality condition is not covered by this. You really have to work about a thing that sort of forces your v to be integers in that case. That will make things integral in the end, as it turns out. Okay, then with Hang, I wrote a paper in 2015 trying to get away from hypergeometric, sort of hyperelliptic curves. So in the end, we end up with the following slightly strange-looking construction. So I basically take products of lines, of equations of lines, and then you sort of deform that. So the product of the equations you make equal to some parameter t. And then it is indexed by sort of taking a certain direction, meaning a point at infinity, ai, bi, and then you just vary the constant for this one. So this means you have parallel lines which intersect at one point. And then you do this for various directions. And then you can take many directions, many points. Important thing is that the genus here will also grow in a kind of strange way if you take many points in many directions. If you get big, that's the main point. And then it turns out you can actually get elements here that are sort of, right? So I have a point at infinity here, and I can have elements that are parallel lengths there. And then take another direction here, and I get something like a square. And actually, it turns out that this combination you can get an element in the kernel of the same symbol. And you can also do something like this if you have another direction. So you just have 3 directions, and you take 3 lines. And you see a triangle occurring here. And you can also put one up out of this one. The first index gives the direction. And here they're all the same. Well, this is the same thing. There's some scaling to make sure the tame symbol is trivial. And then the funny thing is you can actually compute with those more or less geometrically. This one by another line, I cut my square into 2 parts, and the elements in K2 behave accordingly. You get a relation. Right? So that means you can actually calculate with this kind of thing in a, well, maybe unexpected way. And then the point is, if you impose all the relations that you know, then in general, that will be all of them, and you end up with exactly the genus, a number of potentially independent elements. Right? That forces you also to work over Q, because I have to take the genus times the extension of the degree of the base field as the number of elements in the Beilinsons conjecture. So anyway, you get so many, and then you can also, using a limit result, see that, again, if your parameter sort of goes off, so t goes to 0, your curve is degenerating into the lines you started with, then your regulator is going to be non-zero. Okay, but then we didn't do the integrality condition, so slightly better version is if you take 3 directions, or maybe 2, because this may not be there, so horizontal, vertical, and maybe diagonal, and you stick to the algebraic integers for your equation, and the t has now become 1 over lambda, so you get this one. Lambda should also be an algebraic integer. Then all the elements you write down actually in this integral part of the K2. Okay, so if you combine them, then you see that if you use something of this shape, and you fix some parameters and you let the other one go to infinity, then you get something that's integral and going to be independent for a parameter large. And then just to get away from hyperelliptic, there's a criterion of Max Noether, which will tell you when a curve is hyperelliptic. So you can work this out, and then provided my n2 and n3 are big enough, it cannot be hyperelliptic. So we have new examples there. Okay, so that was sort of the introduction. So let's now move on to the paper, the result in the title of the talk. Now, as usual, the way things grow may not be the way to present things. So let me not start at the beginning, but start at a useful point. It turns out that somewhere for the integrality, you are going to need what are called exceptional units. So you take an element u in the ring of integers, algebraic integers, and you want 1 minus u to be also a unit. And well, we want to have such things for, say, cubic and maybe quartic fields. So let's do the cubic first. Well, so of course, if I have a unit in a cubic field, then its equation must be something like x cubed plus some integers plus or minus 1 is a constant term. And then, if you want to bind 1 minus u is also a unit, well, you just plug in 1 minus x as opposed to x, and then you scale by minus 1 to get a monic thing, and it must be essentially the same shape. So that gives you some relation between the coefficients, and that means that basically the second thing, the linear coefficient relates to the 1 for x squared, and an easy way, and with all the signs you get a few choices. You get 4 families in total. Now it turns out that if you take the signs epsilon and epsilon prime all to be 1, this is being well studied, very classical family of cubic fields, which are cyclic over Q, and the other 3 families are not abelian over Q. So you get something that is not abelian. In general, the Gauss closure will be an S3 extension. There are some identification because, of course, if U is a unit, U inverse is a unit, so you get actually the standard copy of S3 acting on Q1 minus 3 points acting on the 4 families. So the one that is cyclic sort of has a symmetry for A versus 1 minus A or thereabout. And the other 3 sort of get identified and also folded, so you sort of get 2 half families that are really independent. Meaning A at least equals something. Okay, so let's look at, well, not the starting point of the paper again. This construction is much simpler than the actual construction, say. So you again write down the clever equation. So you write down what looks like a hyperelliptic curve of genus 2 by taking again something of the special shape we had before, but now this h is actually the square of a linear vector, and if you now were to complete the square of y here, you actually see that you don't get degree 5 polynomial with, well, you do get a degree 5 polynomial, there's a double root. So once you take that one out, you see that the normalization of this curve is actually not the curve in general. And then, well, you can again with, if I put y equal to the coefficient there with a minus sign, again I see I get a point with x equals 0 6 times. So you can again write down some clever elements here, and they're written explicitly. And also the choice of the p, which is one of those acceptable units, is such that somewhere in the discussion you end up with something that is sort of x squared plus, say, 2 minus lambda x plus 1, or so with the lambda there. And the point is, this is actually going to be a cyclotomic polynomial. And that has, the roots are a finite order, and that's all hidden in this construction that you are going to need for the integrality. So that means that the elements you can write down for the lambdas 1, 2, 3, 4 are going to be integral, and again you can compute this kind of behavior of the regulator now. And you find again that sort of behaves like a non-zero constant times the log of your parameter 2, or the rank of your k. Okay, I actually wrote down 4 elements. You can prove a relation among them. So that is the rank of the group is really 3. Right, so I forgot to say, of course, I work over in cubic fields, so I need 3 elements with the genus 1 curve, and that's what you get. Well, you get 4 with simulation. Right, so hopefully this thing will be the group that you write down in terms of those 4 elements with this one relation, hopefully is a finite index in the entire integral part of your K group. And let's see, I think I'm the wrong direction. Yeah, okay. So another thing is actually that for lambda not equal to 4, for lambda equals 4, I think this is stuff, the divisor function are contained in the 6th torsion or your elliptic curve. But for the other ones, lambda 1, 2, and 3, you can see that where the divisor function are in general not in the torsion point. So it's really a function that is sort of intrinsically using the equation rather than sort of underlying torsion point. So let's look at some numerical results. Right, so remember that we had this L function at 0, a star, and this was Q times the regulator of the supposedly finely generated integral K group. And of course, we don't know we have the full thing, but if we believe the conjecture to have something of finite index, so the Q has been replaced by a Q tilde. And then, in order to get the correct Q, we have to multiply this thing here by the index of the group that we use in the full integral K2 that we don't know. Okay, but it means that if you really believe the conjectures, then this kind of thing might be multiplied by some positive integer that is unknown. But it means, for example, that this kind of thing, the denominator here may not be very stable. It may disappear, but at least things that show up in the numerator are going to stay, even if I were to enlarge the K. Right, so, well, this one comes out, the field tends to be totally real, and normally you see a big difference if you go from not totally real to totally real. You do get some big prime numbers. So let me just put this into perspective. If I were to go to a number field, then Lichtenbaum will tell me that this should be equal to the size of k to n minus 2 of the ring of images divided by the 4 prime k to n minus 1. That is the regulator of k to n minus 2 and minus 1. Right, and this is the kind of thing that I would hope that in the future would be formulated. So in 2006, when the first paper about hyperelliptic curves was done in thin was being written, I asked Lichtenbaum what the Lichtenbaum conjecture should be for curves, which unfortunately he didn't know. But anyway, we had a bit of a discussion, but the thing is still not being formulated. There should be something along those lines, but in this case, so one guesses this formula, and I'm showing that this is isomorphic to certain étale cohomology groups, and he suggested to at least use a certain product here over, in this case, 4 étale cohomology groups related to the surface, the model of the curve. But anyway, if you want to think ahead, then it's important to preserve this rational number, get some information about it like this. So that means that if I have a big prime number like this here, it should mean that, well, it wouldn't be exactly this one, but there should be some étale cohomology group of the model of the curve, which has an element of a huge order. Okay, you get the other ones for number 2 and 3, probably similar picture in a way. Because those numbers are not really spectacularly interesting, except for maybe that there is a big prime number from time to time. And yeah, and then also for lambda equals 4. So not very different as far as I can see.
So, what's the meaning of C and D? Is it intrinsic or?
Sorry, D is a discriminant of the. Forgot to say, sorry. So C is the normal conductor.
So there's a curve that has 11 in the conductor and also 11 in the sharp or whatever.
Sorry?
In the next page.
Okay, so D is the discriminant of the field, right? So that's.
Next one.
One more.
Next one more. There's an 11 square and an 11. That seems to be the only case. Now there's a few others. Is that relevant?
Here you mean?
Yeah. Yeah, I was looking at the big primes.
Yes, but I mean,
Oh,
Yeah, but I think that, I mean, well, maybe we'll analyze this a bit more, but I think the only thing I can see here is that the 3 is playing a big role.
well, but the 2 and 3 are gonna behave widely, but the 11,
Well, not always.
you know, this.
No, but I think there is not an obvious relation between the, right, because we, well, in this case, there will be some 6 torsion around the curve, so maybe number 6 should be special, but I don't think that this thing, which, right, of course, there's bad reduction level, but there's no obvious relation between the prime numbers here and the prime numbers there. Right? But, there may be in certain cases, but I think this is probably far too subtle for me to understand at the moment. You can imagine if a curve has bad reduction with a certain above a certain prime, that maybe the Italian homology of the model will somehow detect this, sometimes yes and sometimes no.
Yeah, okay.
I'm happy to discuss those things, but I think that in general you don't get very clear relation, right? Here the prime number is sort of absent almost, and the 5 is there, but it's not in the bad reduction of the curve. And also here, it's not an obvious relation.
Insufficient data for determining. Insufficient data.
Well, in the paper, actually the tables are bigger, but you don't, you don't want to go slide after slide with things. We have about 100 curves in total there, but
Very limited.
Not that efficient.
okay. So let's move on to the second construction, which is in a way the starting point of that paper, but more complicated. So let me first start with something else. So I talked about integrality that we need, and the literature on that is very sparse. So the main thing that actually is known is sort of a non-integrality criterion. If you have an elliptic curve, and you take a nice standard minimal model of rho prime p, and suppose you actually get this kind of an n-gon, so this in general will be, I think, I n or something like this. And then there is actually a criterion for, say, elements like this, what happens, which components they hit, right? I have O here, which sort of hits the 0 component, say here, and I have a point P, which hits maybe another component, I have a point Q, which maybe hits another component in the special fiber. And there's actually a criterion for non-integrality in this context. So it will tell you when things will not relate to the L function, hopefully. So this criterion, it will involve the third Bernoulli polynomial, because you sort of count where in your n-gon you are, and then this will dictate where what comes out in terms of the torsion obstruction, or non-torsion obstruction. So the kind of obstruction in here will be from K2 of, in this case, your P, or the tame symbol, maybe there, and then it goes to K1 prime of, in this case, your fiber. And this is sort of easy to describe. Certainly if I take the kernel of the tame symbol, because then I get certain quotients, it will, roughly speaking, correspond to having functions, non-zero functions on each component. And if I compute the divisors at the points where the variance component intersect, they have to cancel the zeros and poles. So that is the obstruction that is mentioned by the criterion that I just mentioned. It sort of mentions the order of the pole here, and if the order of the pole is 0, then you can still have all kinds of torsion functions, constant functions on the component. So there's kind of a torsion obstruction that you're still left with, even if the actual obstruction vanishes. Anyway, we wanted to do a little bit better in the current paper, and due to other things in the paper, we ended up with the following criterion. So let me just summarize. If a nice model, if this from the torsion points O, P, and Q. Suppose that N, P minus NO is divided for F, and similarly for G with Q. And then really it depends on how many of the components in your fiber you're going to hit by O, P, and Q. So this basically says if O, P, and Q all hit the same irreducible component in the fiber, then the tame symbol for every component in your fiber is going to be identically 1. So not just torsion, it will just be identically 1. And if they had 2 components, then it is going to be constant on each irreducible component, so that will make a torsion automatically. But you can be a bit sharper because you get an obstruction in terms of root of unity. So if you divide your function v by f is not something that is defined at all, but its value there will be n for the view. And then the image modulo your prime is basically going to be the order of the obstruction on at least a large part of your fiber. If you do the combinatorics of this game, you see that you may not get information on the entire fiber, you get information on a large part, at least for the actual exponent. Because in general, if you have a constant front d, of course, you can just compute what the exponent could be based on the prime. And well, the good thing is, because in the end we want to have elliptic curves, this certain part of the fiber will always cover the entire fiber. You just sort of look at the description of the part, you look at the possible reduction, and you see that in that case you're lucky, you get everything. So that means you get a really, even if you hit two components, you get an explicit exponent for the obstruction to integrality there, provided you hit at most of the components. Okay, and then just, well, this is an example that tells you that this obstruction can be non-constant on the fiber. So in this case, you take a curve with a 6 torsion point. This one will have divided with 6 times p minus 6o. This one will have it with p replaced by minus p. You then just compute what's going on. It turns out that for the prime 3, your reduction consists of 2 copies of p1, which are tangentially in one point. And then the tame symbol at only 2 components to hit, so the obstruction will be torsion. And it turns out in this case for the 0 component, I think it's minus 1, and for the other component it's 1. So obstruction for the 2 here that you have to live with. So I have to multiply this element by 2 to get an integral element, at least for the prime 3. Okay, let's now switch to the full construction with this integrality criterion. So I told you it's easy to create elements in the kernel of the tame symbol if you have points on a curve with the difference being torsion and Jacobian. So on elliptic curves it's kind of easy, you just take a point for the n, and in the subgroup that it generates, you'll have lots of differences that will have this property. So you do exactly what I said before in this context here. I take a multiple s times p, I write down a function that has the polar for the n at sp, sorry, 0 for the n at sp, and the polar for the n at o, and I normalize this function to be 1 at, well, the other point tp for the n at o. So this is automatically going to be in the kernel of the tame symbol. And then for historical reasons and symmetry, you sort of take not just one of those, which involves only 3 points, you're sort of going to sum over, say, the S to make it more symmetric. This is actually what happens in Spencer's original work. And then also I throw in a trivial element to just make sure that it provides what the functions involved are a bit more symmetric. Right, and then that means that by now, because I sort of averaged over one of the S's or T's, then I have sort of S, I can let 1, 2, 3 up to n minus 1. But you can actually see there is some symmetry involved. So translation and multiplication by minus 1 will sort of more or less act in the way you think they should be acting. And that means in particular that if I use, say, S times P or minus S times P or so, then that will give me a relation. So I sort of get only sort of half the elements that I expect, at least modulo torsion if I work over a number field. So if I think, for example, that I want to have something over a cubic field, then the minimum that I need for my n is 7, because then I can get potentially 3 independent elements. So let's look at curves with n torsion point over the n. So if this order is at least 4, you can write down a unique Weierstrass model, at least in a particular way, the take normal form, that gives this point coordinate 0, 0. And well, the explicit shape is sort of known for various n. So in this case, we do this on the modular curve, open modular curve x, y1 n. Right, so we have a universal family with an n torsion point there, And then we stick to the situation where we can easily write down maximal points on the base modular curve, so it's genus 0 in practice. So that will bound the n, but we didn't want n to be too small, and it needs to be 7. So these 5 values, 7, 8, and 10, which we deal with, and then 9 and 12 you could deal with in a similar way, but then it's a little bit more complicated, so you just ignore it. Anyway, so for the modular curves for y1, 7, 8, or 10, the Tate normal form of the universal elliptic curve is known, so written in terms of those b double f and f and g. And you see that in this case, if you have a certain parameterization of your rational modular curve in terms of t, then well, you can sort of see that t and 1 minus t are going to be moving as a very unit. That's probably pleasant here. And something like this holds for 8 and 10, but in a more complicated way. Anyway, so you have a family with prescribed point order 7, 8, or 10, and you can write down the elements I just had on the previous slide. And well, then you may wonder when those things are going to be integral. They will be in the kernel of the tame symbol, but I want to be on the kernel of the tame symbol on the entire model of the curve. So, well, we just had a nice criterion for this in terms of where the points on your bed fiber lie. So you can actually check that if I multiply them by 2, then you're always going to hit a 0 component in your model, provided you impose a few conditions on your parameters. So for n equals 7, you need t and 1 minus t to be special units, right? So then we go back to the exceptional units, so that means we go back to the special cubic fields in that case. For n equals 8, it's a small variation on the theme. It's basically the same kind of thing, but then a different relation with the t. And then for n equals 10, you get a slightly different one. Okay, so, but if I go for n equals 7, I told you that 2p always hits the 0 component. That means p hits the 0 component. In the elements always just going to be integral. And if n is even, then, well, if you go back to the criterion, I have to worry about some order of roots of unity, but if I multiply by a suitable integer, then I will get integral elements. And the integer is very well controlled. So there's no very big surprise there. Okay, so as I say, if you look at what happens for n equals 7 and 8, you are just forced to use, if you use a cubic field, to use one of the earlier special cubic fields. And then for n equals 10, well, you can get 4 elements, so we want to have a quartic field. And then, well, you also get a relation which sort of if 1 minus 2t is a unit, then either one is a unit there. And that gives you, if you work it out, a bit more complicated for the cubic one, it will give you 40 families of such fields. And let me put in the table and answer for a second. But in general, the Galois closure of this quartic field will have S4 as the Galois loop. In 28 out of the 40 families, in general, there will be in a family finding many exceptions. It can be dihedral for the 8, cyclic for the 4, which is also a classical family, and cyclic, well, sort of Z2 plus Z2. So anyway, you get a big table if you work this out. And the only thing that is important is that you have again such a general quartic equation with constant term plus or minus 1 and integral coefficients. And then the correct behavior for this, 1 minus 2t and the other one 1 over t minus 1 to be both units to give you some relations among A, B, and C. And well, this is the summary of this thing. If you have a large pot of coffee, you can do it. They're kind of annoying. And then you can have criteria for the Galois closure, and you can just go through and see if you get 28 times S4, etc. Okay, so that means we have now for the Tate normal form for the 7, 8, we have root cubic fields that may be cyclic or may not be cyclic over Q. And for n equals 10, we end up with those 40 families of quartic fields. Okay, so let's summarize this here. Okay, so we for n equals 7, we take one of those special cubic fields, and we had a polynomial which had an a in it, a cubic polynomial with an a in it, and u was a root. And then for n equals 7, the parameter t for the elliptic curve had to be an exceptional unit, and that we can just put to the u. And then for n equals 8, it's a small variation, it has to be 1 over this unit plus 1. And then for the quartic one, we have the families that we had on the previous slide. And then we have to use a unit of the root of the polynomial, and then you have to have this particular t in the equation of your elliptic curve of the 10 torsion point to get our elements to be in the interval k2. Right? And then, well, you have to keep track of all the multiples, but basically either 1 or 2 times the elements that we started with will be integral, and then you can actually sit down and you can compute the limit of your regulator. Everything is parameterized by a in this case. I forgot to say that if a is sufficiently large, then your field is always going to be totally real in all those families. So that means for any 7 or 8, where you're going to get 3 independent elements in if a is large enough, and then you can calculate the relation or the pairing between the explicit elements in the K group that we have and the elements in H1 minus of the union of Riemann surfaces, that you have to calculate what the basis is of that one. And then you end up with this expression. The important thing is this determinant is non-zero. And in fact, Fernando told me that the whole starting point of the paper was that the fact that there's a B3 here, which we'll see in a later slide as well. And he said, hey, there's a B3 in this integrality obstruction here as well. Maybe there's a relation. And from that, you basically sort of constructed those quartic fields and the cubic fields that you actually need. But in the end, it's done in a completely different way, but it was the entire starting point.
But here n is always 7 or 8?
Or 10.
Or 10. So when you say the determinant is non-zero, just in those 3 cases, or is it never 0?
Sorry?
It's determinate. It's always non-zero, or just by calculation for those 3 n?
Oh, you mean for all n?
Yeah, I'm just curious.
We check it for n equals 7, 8, and 10.
Okay, so you're not.
But it may well be that it is non-zero for all.
But most numbers are non-zero, but I want.
That's certainly correct. Yeah.
It's likely to be non-zero because it has to do with the constant term of Beilinsons series, and so I think it must have a meaning. It's not a proof, but
this thing is
Might have written
Huh?
those form.
Have you checked?
no, I haven't. But I'm just thinking as you asked that it's unlikely to be
It
zero.
looks like a very nice determinant.
It is, but it's.
But you've only looked at it for 3 values.
Well, I think we had enough trouble to get there, and then this one is. We were happy that it is non-zero for the values we wanted. But yeah, you're right. We thought that it might be non-zero in general. Actually, this is one of the reasons that we used going back, right? Because we said those are actually the simplest elements to use in the tame symbol because they will involve only 3 points. If you then were to compute a determinant for those elements, right, you take some of those, then you end up with a big mess. It will be related to what we have now, but it wouldn't come out as clean. Anyway, so that is one of the reasons to actually go to those sums of simpler elements to get something simpler here. Anyway, so that means that you now have in all those families, right, I can take a non-Abelian cubic family for, sort of the ones that we had for n equals 7 or 8, and then in the longer run, if I let my parameter go to infinity in absolute value, you get elements that are integral, and they have they are independent because it's regulated, it's not non-zero. In fact, you get some kind of behavior compared to the log of the parameter. And the same thing for the quartic fields for n equals 10, right? And we had 40 families, 28 for Gauss closure S4, so there's lots of non-Abelian things with expected 3 or 4 independent elements. So we got away from the Abelian things that I was indicating in the beginning, where you always end up if you work with modular curves, basically. At least modular in another way, because we just use the modular curve as a nice way of writing down the fibers, but we don't really work on the modular curve itself for constructing the elements in K2. This is just done sort of in every fiber. Okay, so why would this work? And I think this is not, it's a little bit too detailed to do it in any detail. But in the Irvine notes, when Spencer wrote down his element in K2, the kernel of the tame symbol on the curve of Cm over Q, he used the Dye logarithm to create a regulator map. So the Dye logarithm has been introduced already several times, so let me not do it. But then if I view my elliptic curve, or at least its complex value points, as C star modulo power of Q, then he simply took the Dye logarithm and he Q averaged it. Because of the behavior of the Dye logarithm around 0 and infinity, it's so heavily converged. And then you also needed another part. So this is based on, again, log of z and log 1 minus z, like the dialog, but in a different way. And then you can also define a sort of Q average version of the J, then it would not converge so nicely around infinity. So you just let it go to where Q is supposed to be smaller than 1. So this would be nice around 0, if z goes to 0, basically the power is z times q to the power n. And then you sort of impose the functional equation for z versus 1 minus z, and then you end up with this expression with, again, the third Bernoulli polynomial coming in. So if you then look at your curve as C modulo a lattice rather than C star modulo the power of Q, you also get the Dye logarithm, but then sort of in terms of the tau rather than the Q. And okay, so we need to know something about the pairing between an element in the kernel of the tame symbol and a loop. And this is actually known. So this is, I think, also in the Irvine note still. So your functions f and g in your functions, they have a divisor, of course. And then this star product of the divisor is basically a convolution product. So you take the difference of the elements and then you multiply with the coefficients. And then the and that is the number only of the point on the elliptic curve that you then, or to everything in the sum, every ai minus bj, you apply your elliptic diagonal and then you multiply with the coefficient, right? So you just extend the r tau from the curve to formal combinations of elements in the curve. And then it turns out that if you pair your alpha, right? The alpha gave rise to a long form eta. And eta we integrated over the loop, divided by 2 pi, and you can actually rewrite this thing in this shape. So the important thing is this elliptic dialog, and then you get some periods. So there is a standard period from 0 to 1 based on your parameterization, basically, a C modulo z plus z tau. And then the other period you have is based on the loop gamma that you have. Right? And then again, if you because you chose the element nicely, if I pair it with this standard loop, then of course you can see that omega gamma and omega gamma 0 are going to be the same. So it means the entire thing will simplify a lot. Only you're going to see the imaginary part of your r tau, which is the j. So that means you actually only see the j, and then again the device comes out very cleanly in this case, and you get a very simple expression for that one. Okay, and then you have to analyze what's going to happen in your entire construction. Right? So we have this parameter a in the polynomial, and we let it run to infinity in absolute value. And that means in practice, if you look at which curves you have on the modular curve, you're going to run towards a cusp. And of course, it depends on which route you take, which cusp you're going to run into. But then if you look at what this j behaves like, then, well, again, the dominant part, if y goes to 0 in this case, is going to be, y goes to infinity, again, is this, has something like the third Bernoulli polynomial. That's the one you actually see in this determinant. Right? So I think I can sort of try to summarize this a little bit, that you need to know that that's totally real, so you can sort of fairly easily at least describe the h1 minus of your elliptic curves. You have to know if you take your roots and embedding which cusp you're going to approach. And then, yeah, you have to understand complex conjugation everywhere. Okay, so that gives you this theorem. We also did a few computer calculations again. So for 7 or 8, we had this earlier cubic non-Abelian thing. And then we have the probably elements sp1, 2, up to 6, but as I say, there's some relation, so you can't do the first 3. And then for n equals 8, you do the same thing, but we have to multiply them by 2 to get integral elements. And for n equals 10, well, we took this particular family out of the 40 options we had. So it's not an S4 thing for the Gabor closure, it will be diagonal of order 8. And again, it tends to be totally real, not always. And then in this case, we use those elements for the rational number. And you get 3 slides, right? N equals 7, 8, and 10. I think you can see from the rational numbers that 7 plays a role here in the construction. Right? Point of order 7. Again, you're going to end up with some bigger prime numbers as you go away, so they should be, well, have some interpretation that we don't know yet, but there should be something interesting there. N equals 8, prime number 2 playing a big role, and again, you're going to get some very big prime numbers. As the parameter increases, then n equals 10, where 2 and 5 play a role, and the big prime numbers are completely missing. For I don't know what reason.
13.
Sorry?
13.
Yeah, okay. Right. Depending on your depending on your definition of small or big and things like this. Anyway, so but if you go back a little bit to start finishing up, if you go back to the integrality criterion that I gave you, right? The additional one is sort of something that was based on the simple f comma g with a very special shape. And the element that is actually based on this s, the simple s, is actually a sum of such elements. So how do we know that the s is integral? We know this because I take a sum of integral elements. And this is overkill because maybe a different sum of non-integral elements will produce an integral element in the long run anyway. So that means you can then sort of go back and maybe make the group a little bit bigger. Right? And then, okay, let me just cut a little bit short because I could have A, use maybe the elements separately. B, for example, if the 7th torsion point, I can first just write down an element in K2 using only functions that have divisors in the subgroup order 7. And then I can check when something is going to be integral. That means I can get a larger group, and that means you can actually multiply the rational numbers we have by 7 to the power 6 for n equals 7, or 7 to the power 5, and it's totally built, so in general, or 2 to the power 10 equals 8, and 2 to the power 10, 5 to the power 4 for n equals 10. So if you then go back with 7 to the power, say, 5, 2 to the power 10, and that thing, so if I multiply it by 2 to the power 10, 5 to the power 4, it will not clear out all the denominators, but it will certainly simplify things a lot. And here it was 2 to the power 10, right? So again, well, I think most will almost always be the denominator, but it gets a lot better. And then here 7 to the power 5. So this is really going to be a lot better. Okay, I think that was the
Just thank Rob.